Hi, now let's do some energy examples. First, I'm just going to go back over the stuff you hopefully learned in the previous lecture, just in case, so things are in the same place. But I'm going to be quick about this because it's mainly about the examples. So, in the last lecture, we learned that work is equal to the force times the distance, and work and energy are in units of joules. We also learned that power is the work done over a time interval. So it takes more power to do the same amount of work in half the time, or it takes less power to do the same amount of work in twice the time. And this power has units of watts. Then we learned about gravitational potential energy, which is the weight of an object times the height it is off the ground. And we use this equation, potential energy, PE, equals mgh, where m is the mass, g is the acceleration due to gravity, and h is the height off the ground. We also learned about kinetic energy, which is the energy of motion. And that is given by 1/2 the mass times the speed squared. So it's like 1/2 the mass times the speed again. We also learned about the work energy theorem, which says that the work is the change in kinetic energy. And so because of that, we can say that the force times the distance is equal to the kinetic energy, or the change in kinetic energy. Okay, now that was real quick. So go back to the other lecture if you need more. So now we're gonna do some examples. We'll start with this one. So we have 3 vehicles, and their masses and speeds are shown, and we want to rank them over the following top items: momentum, kinetic energy, and the work done to bring them up to their current speeds from rest. So let's take a look at this. Okay, here we go. So let's write out some things here. We know the equation for momentum is the mass times the velocity. Feel free to write out the variable names if that's easier for you. I just don't want to take up as much space on the page. And then the kinetic energy equals 1/2 the mass times the velocity squared. And then the work is the change in kinetic energy, or it's the force times the distance. We'll figure out which of those we want to use to solve this. So first, it's asking us to rank the momentum. So let's just calculate all of their momentum. Momenta, I think it's actually the plural, but it's okay. We don't have to use the proper plural. So momentum for A, we have a mass of 800 kilograms and a velocity of 1 meter per second. So that gives us 800 kilogram meters per second for the momentum of car A. Then for B, we have a car that is 1,000 kilograms, and it's moving at 2 meters per second. So that's going to give us 2,000 kilogram meters per second. And finally, the bicycle, just a mass of 90 kilograms, very small, but then a speed of 8 meters per second. So, 1, 2, quickly, 8 times 90. That gives us 720 kilogram meters per second. So that's actually pretty close to car A, but it's still smaller than it. So let's rank these. Car B has the most momentum, and then car A, and then car C. Or C isn't a car, it's a bike, but you get it. Okay, and then it asks us about the kinetic energy, or to rank the kinetic energy specifically. So let's see. Kinetic energy of A, that's going to be the same. Oh, don't forget the 1/2 in front. Same mass of 800 kilograms. And then the speed is squared, 1 meter per second squared. So this is going to give us that 1 squared is just 1. And then we are just dividing 800 by 2. So that gives us 400 joules. Remember, that's the units of energy. Okay, let's look for B. 1/2, and this one was 1,000 kilograms. And the speed is 2 meters per second squared. So that gives us, I'm going to do the math of the first two. I'm going to say, okay, 1,000 divided by 2 is 500. We'll keep the units of kilograms there. And then we're multiplying that by 2. Oh, no, we're not. We squared that too. We're multiplying it by 4 meters squared per second squared. You got to give those units the square treatment too. So 5 times 4 is 20. Plus a couple zeros, 2,000. 2,000 joules. Much bigger than part A. So you can see already how much squaring the velocity really changes things. And then finally, the bicycle or vehicle C, I suppose. So that's 1/2, and that's only 90 kilograms, so really small, but it's going really fast. It's going 8 meters per second. And that's going to, especially when we're squaring it, that's going to be big. So we have 4.5 kilograms when we, 45 kilograms, excuse me. I was thinking 9 instead of 90. 45 kilograms when we divide 90 by 2. And then 8 squared is 64. So then we just want to know 45 times 64. And that is 2,880 joules. So that one makes it bigger than B this time. Actually, the biggest. So the most kinetic energy goes to the bicycle. This is actually just in reverse alphabetical order because next comes B and then finally A. Cool. Now for the last part, it asks us the work done to bring them up to their respective speeds from rest. So we have this relationship, but let's just take a look at this. Let's do a different color. So the work is the change in kinetic energy, right? So that's the final kinetic energy. So what it is at right now, minus the initial kinetic energy. And the question says, bring them up to their respective speeds. So that's, the final side from rest. So initial is actually just 0. So what this tells us is that the work done is actually just the kinetic energy we're dealing with. So the ranking for part C is actually the same as the ranking for part B. There we go. Awesome. Let's look at the next example. Okay, for this example, we have my beautiful drawing. Promise there's a much better diagram of this in the slides if you want to take a look. But what we have are 2 people moving blocks of ice. So for the first part, the first question asks how much work is done in lifting a 100-Newton block of ice a vertical distance of 2 meters. So that's this one on the right, is just lifting it up to the top of this ramp, just vertical distance of 2 meters. So let's look at different color. We know the work done, right, is the force times the distance. So we'll just plug those in. 100 newtons times the distance of 2 meters. So that gives us 200 Newton meters or joules. So that's the work done for question 1. Then question 2 asks us, how much work is done pushing the same block of ice up a 4-meter long ramp where the force is only 400, or sorry, wow, just making up numbers, is only 50 newtons. So we just do the same thing. This time, 50 newtons instead of 100 and 4 meters instead of 2. Well, would you look at that? That just gives us the same thing again, 200 joules, which makes sense because we're just moving it up to the same spot, right? So the last question asks, okay, what is the increase in gravitational potential energy in each case? So gravitational potential energy is mgh if in both cases, it's 100 Newton block of ice. It's just that when it's on the incline, you don't have to apply the full force of its weight. So this part is 100 Newtons in both cases. And then they're going up to a height of 3 meters, I believe. 2 meters, sorry. No, I just did it. But... So we get 100 Newtons times 2 meters gives us 200 Newton meters or joules. So those are all the same. So what we see here is that the work done is also equal to the change in potential energy of our object. Okay, last example is a roller coaster. So we have a roller coaster that starts from rest at position A. Remember, starts from rest means not moving initially. And we want to rank these quantities from greatest to least at each point. So the speed, the kinetic energy, and the potential energy. We're actually going to do this one in reverse order. Like we're going to do part C first because I think it'll be the easiest. So potential energy is mgh. So if it's the same roller coaster car, right, that's the same the whole time. The only thing changing is the height. And this, at position A, that's definitely the highest. And then position E is the next highest. And then C, and then it looks like B is slightly higher than D. So D is going to be the lowest. Because that tells us, okay, D has the least kinetic energy. So this is part C. I know we're going backwards and I'm even doing the least first, but I'll put it over here. So D, and then B was the next one, and then C, and then E, and then A was the biggest. So that is the potential energy. Potential energy. Okay. And then I think we'll just kind of combine A and B. Actually, no, sorry. Changing my mind. We'll do B first. So what do we know, right, about the kinetic energy in relation to the potential energy? Well, it's kind of like they split it up, right? Because the total energy is the kinetic energy plus the potential energy. So up here we have the maximum potential energy, max. And that means we have the minimum kinetic energy, minimum. And then we have the minimum potential energy at D. Potential energy is a minimum. So that's going to mean the kinetic energy is a maximum there, right? So what we find is we've labeled our points where we're at our maximum kinetic and minimum kinetic. And that is actually just showing us that, you know what, the kinetic energy is actually just going to be opposite of the potential energy. Because this is where the potential energy is like the next lowest, which means the kinetic energy is the next biggest, and then C after that, and then E, and then all the way back to A. So E has some more kinetic energy than A, and then C, and then B, and then D with the most kinetic energy. And then finally, we're on part A. I know I keep doing things backwards, but that is connecting us to the speed. And this is where we can say, okay, the kinetic energy is 1/2 the mass times the velocity, or speed squared. So if these two parts are the same the whole time, it really tells us that where the kinetic energy is a maximum, the speed is also a maximum. So actually the answer here is this is the same rating for kinetic energy and speed. So let's take a look at that. Let's say, okay, we have the least speed at the start. Also because we know it says it starts from rest. And then we have a whole bunch of speed at B, and then we slow down some when we go to C. And then we speed up the most at D, and then we're slower again at E. That's our ranking. I hope that makes some sense. Feel free to reach out with questions. That's all I've got for you.